Right. So in 12.2, we looked at fluids, but we looked at fluids that were stationary. The fluid itself wasn't flowing. Although we described the fluid as something whose particles could easily or readily flow past one another, it was at rest. A lot of our problems involved equilibrium. We talked about buoyancy and density, but things where fluids were at rest. This section differs because things are now in motion. We're going to talk about what's called the continuity equation. How many of you live in a suburban area that have a decent size like backyard that you might have to do stuff in the backyard? Do you all live in the city in the room? Anyone? No? All right, well, if you're in your backyard, you had a garden in the backyard, right? So imagine you're in the backyard, you want to go water the garden. You take a garden hose. What do you usually put on the end of the garden hose in order to make it work when you want to water something?
Like the nozzle.
A nozzle is the word, okay? Yes, listen. It can be called a sprayer, but a nozzle is the real word. Sprayer works too. A nozzle, all it does is redirect the flow. It changes the amount of cross-sectional area, which increases or decreases the velocity. And you've seen on the back of it, there's usually a little dial that you can turn to make the water either shoot out further or spray like a mist. And that's going to be explained by what's called the continuity equation today. It's the same reason if you've ever seen firefighters. Ever seen a firefighter actually putting out a fire in a building? Those firefighters, the water can reach up to like ridiculous heights. It's because the end of the fire hose is tapered, and they can adjust the cross-sectional area of the end, causing it to either spray further or shorter distances, but there's more or less water flowing. Okay, so we'll see that. We'll talk about what's called Bernoulli's Principle. If you've ever wondered how you can fly, Bernoulli's Principle explains flight. Literally explains the concept of lift force, why you can lift off the ground. And third, we're going to talk about turbulent and laminar flow. And there's a number you can measure to determine if something that's flowing as a fluid has a predictable motion or something that's erratic and the behavior cannot be easily predicted to where it will lie. It's actually, the number is called the Reynolds number. The Reynolds number. Last year I had Tom Reynolds in class, and the fact that his name was named after something. It's a number that you calculate. If it's greater than that, it means the flow is too turbulent or unpredictable. If the number is less than the value of the threshold, it means that the flow is steady and laminar. So let's describe these words. Laminar simply means it's a smooth, predictable path. A smooth, predictable path. Turbulent means it's irregular, unpredictable fluid flow. So if you've ever seen in like a river, imagine you have a bird's eye view and the water is flowing in this direction. And there was like some rock in the middle of the water. As the water flows into this rock, what happens to it? Imagine the rock is sticking out of the water. It's a big enough rock that it's not fully submerged. Yeah. You see it's like this, where the water goes around it. Now, after that rock, sometimes there are little things called eddy currents, where you see like God bless you, you see little bits of turbulence. These are called eddy currents. And the whole idea here is that the flow before being interrupted, bless you, is smooth, laminar flow. It is predictable. It follows a steady streamline the whole way. When it hits something that causes its path to diverge, sometimes it causes turbulence in little pockets. On an airplane, this is physically what's happening. The airplane is flying into the wind. If the wind itself, if the conditions themselves are bad enough, you get these sorts of currents or these eddies that cause the plane to kind of jump. If you've been in a plane before and you notice turbulence, you feel like shaking. That's literally little pockets that are causing the airplane to move. How come it doesn't just go off course and veer off to the ground? It has automatic stabilizers. Those little flaps on the wings have a response system that can sense the smallest amount of change in angle and automatically adjust to level back out. That's why turbulence doesn't actually really... So if you were on a plane like the Wright brothers invented, and you were up that high, turbulence would easily kill you. You wouldn't be able to actually... Your plane would not be able to withstand unless you have turbulence there. But it has stabilizers on the side of it, which causes it to negate that almost, or counteract it. It's called the feedback system. It's an instantaneous feedback system. Do you remember? I don't know if I showed this section or not. Did I show you guys the video of the Big Bang Theory with the little algorithm? Yeah. Did you see that? Okay. Imagine a feedback system that has a little circuit like that, like a block diagram that says, if the pitch of this wing is too high, automatically adjust this flap. And then there's another outlet. If it's too low, adjust this flag, etc., etc., etc. It's a bunch of switches or if statements. So that's the idea behind what turbulence is. It's flow that's erratic.
So if a current went this way, so then the eddies just like reverse it?
It's not necessarily reverse. The symbol here just means flow that is not predictable.
Oh.
Okay, that's all that symbol really means. It's just like, ever see water like churning?
Yeah.
In like, has anyone ever gone whitewater rafting before? You know when the water like churns like crazy and you can see the foam coming out of the water because like it's actually moving so much, you see the air pockets? That's the kind of turbulent flow we're talking about, where it would like literally like not necessarily pull you under, but it would be difficult to navigate through. There's an app if you want to pause before we get to viscosity and ideal fluid. Let's resume now. So the other two words are viscosity and ideal fluid. So viscosity, here's how you think of viscosity. High viscous means it doesn't flow very easily. Give me a fluid that flows very slowly. Think about if you're cooking at home and you might want to use a fluid that could flow very slowly. Syrup is a perfect example. I think of it right, think about pancakes or waffles right away, right? What else? Honey, which is syrup, right? For tea, for cooking in general, like if you cook fish, honey is very good with that, right? You may know that one. Honey is very good with it. But it's so annoying to get out of the container. Why? Because it's very viscous. Viscous. The viscous force is physically the force of resistance between those sticky particles, between those particles that don't want to separate or flow very easily or readily. Okay, so high viscosity means very, very slow flow. It's very slow flowing. There's a lot of friction between the molecules themselves.
So low viscosity is like water.
Sure, yeah, there's better stuff than water, but that would be a good example relative to honey and syrup. Water has a lower viscosity than those, but there are lower viscosities than water itself. You got a hand up real quick.
I was going to say tar.
You gonna say?
Tar.
Tar?
Yeah, that's the kitchen. No.
Like molds and stuff.
Tar, like, when you cover
I think you use like molds and stuff, like when you're barbecues with concrete.
Okay. I mean, if you do work on cars and stuff, if you do work on cars, you get a lot like, what is that called? In the bottom of the gasoline tank, the sediments that settle out, it's called like crude oil, the stuff that's really like sticky and difficult to get off your hands. That'd be an example, and that's very tarish. An ideal fluid is something that is not viscous. So honey would not be an ideal fluid. Not viscous. When flows, if there's no turbulence in the flow, and it's incompressible. Remember, it cannot be compressed. We talked about that in the last section. So a lot of the time, Newton's laws that are used in fluid flow assume that there is an ideal fluid that is flowing. So the assumptions are huge. Remember how we talk about like we assume no friction? Remember with air resistance, when projectile motion, we said there was no air resistance when an object flew through the air. It's a very ridiculous assumption to make because we know there's air resistance for sure and it does affect the trajectory of objects. Same thing here. An ideal fluid can be used to model things, but a lot of the time the fluid flow is not necessarily ideal. If you have a system like an air conditioning system where there's a refrigerant is a fluid that flows through a cycle that absorbs that heat, that allows it to cool the air. That's an ideal fluid flow. It needs to be for the laws of mechanics to work for this. All right, let's talk about the continuity equation. Can I get rid of that? There we go. The continuity equation. This explains why when you use a nozzle at the end of a garden hose, the water can shoot further or it could spray. So the idea is this. If you have a change in the cross-sectional area, and you've done this before, have you ever put your thumb over the end of the garden hose? What happens to the water? It sprays out when you put your thumb over the very end. It's the same thing as this. So this flow, in this case, just so you can see, this is demonstrating flow this way, okay, from the left to the right, but it doesn't have to be in that direction. It could be from the right to the left. But the idea is that if you change cross-sectional area, the velocity itself changes. And look at the equation. It makes sense. The equation here says that at any given instance in time, the area times velocity, this is velocity, write yourself a note, this is not volume anymore. In section 12.2, capital V was volume. This is lowercase v for velocity. The area, or the cross-sectional area, times the velocity at one instance must equal the area times the velocity at another instance. So if the area goes up, for this to remain true, what has to happen to the velocity at this point? The area goes from a small area to a really big area. So what has to happen to the velocity? If area goes up, this number goes up, what has to happen to this number for this to stay the same? It has to go down. So again, if this is some value, let's pick an area. Give me an area 1. I don't care what it is. Thank you. Give me a velocity 1. All right. So A1, V1 is 50. Does everybody agree with that? A1 is 5, V1 is 10, A1, V1 is 50. Now, the next area has to be greater. Give me a number greater than 5. 7. If area 2 is 7, well then I've got a 7 here. What must V2 be? How do you solve for V2? Obviously divide by 7. It's approximately 7 also. That's just a coincidence. But what's the idea here? The idea is that the velocity had to go down from 10 to 7 because the area went up from 5 to 7. It just happens to be approximately, it's really 7 point what? What's 50 divided by 7? 7.14, thank you. So we can see that it's not the same answer. Okay, airplay is delayed, guys. There it goes. So velocity must decrease because the area itself is increasing in this problem. The continuity equation is like the conservation of momentum equation. Think back to momentum. M1 V1 before the collision had to equal M2 V2 after the collision. If something went up, something had to go down. Do you remember the problem with there was a train and snow kept accumulating on the train? And I said, the momentum is constant though, and the mass is increasing because the snow keeps accumulating. If the momentum was constant and the mass kept going up, the velocity had to go down. There was that balance there. Same thing here. The flow rate is constant in any pipe. So if the area goes up, the velocity has to go down. The flow rate is called the volumetric flow rate. This is really important that you understand this. When you fill up your tank at the gas station, the volumetric flow rate is how many gallons you're pumping every minute, or gallons per second, or whatever you want to use there in units. But it'd be gallons per second. Here, if we take a look at this, what are the units of area? I'm going to go back up to the top for a moment. What are the units of area here? Area. What is it?
Meters squared.
Meters squared. What are the units of velocity? Come on, guys, you know these. Please, let's go. Okay? Meters per second. Now, if I take a look at this, I end up with meters cubed per second. That's what that'll become if I multiply those two together. Does everybody see that? Literally. Meters squared times meter is meters cubed. What is meters cubed, though? Isn't that a volume? And a volume over a time period is called volumetric flow rate. Remember, I talk about rates a lot in this class because almost everything in physics and even going on to calculus is a rate. So this is the volumetric flow rate we're talking about here. Okay, the volumetric flow rate itself is always constant in a pipe. So that's why when we change the area, we have to change the velocity itself. Okay, the volumetric flow rate. Okay.
So is the unit AV or is the unit?
The formula is A1 V1 equals A2 V2. But the units of A are meters squared, the units of V are meters per second. That was just proving what it was. Okay? But the formula itself is just AV. So let's take a quick look at an example. This is easy, but don't fall into the simple. There's a common mistake here that a lot of people make right off the bat because they try to jump into the problem.
Centimeters gets converted to meters.
That's one thing. Sorry, it's two mistakes then that can be made. Centimeters should be converted to meters. What else? The formula calls for area. Are you given the area? Thank you. You're given the radius. What's the area of a circular pipe? If you're given a radius, you know it's circular. You don't have to, it doesn't have to be told. How do you find area when it comes to formulas? Formula for area. What is it? Pi r squared. So that's what this will look like here. You don't need the parentheses. I'm putting them there to show you that I've substituted for the value of a with pi r squared. Parentheses are not necessary. Please don't distribute accidentally. There's no plus sign involved. Now, if pi is on both sides, what does it make sense for me to do? It makes sense to cancel them instead of getting some irrational decimal and having to deal with that the whole time. Now, that gives me a formula of r1 squared v1 equals r2 squared v2. So this is just another version of the formula at the top. Except now the values are squared, which makes sense because a radius is given with a simple unit of centimeters. It has to be squared to make it an area, so it's a square unit. So this is 4 centimeters. So we know that the radius is 0.04 meters. That's what Ernest told us, right? We got to convert to meters. Turns out the velocity to start is 5 meters per second. It says, what should the radius reduce to? So what are we looking for? We're looking for the radius if the velocity is to double. So what's the velocity going to be? 10. Okay. What did you get? Careful.
Oh, 8.
Okay, we got to solve for R2, so go ahead and plug in and solve for R2. Okay, it's just a plug and chug at this point. You know R1, plug it in, square it. You know V1, plug it in. You know V2, solve for R2. What's that?
Why is the velocity? Oh, it's not.
Okay. Hey, if you want to challenge yourself, you think this problem is a little easy, instead of using 5 and 10, you could just use V and 2V. Right? If a velocity is double the other velocity, you don't have to give it a number. Theoretically, I'll put a little side note if you'd like to. You could have done this too. Look, you could call the first velocity V and call the second velocity double that. See what I'm saying? Instead of actually using numbers that are given in a problem, if the second velocity is double the first, call the first one V, like we called things M before. And if another object has twice the mass, we call it 2M or 3M. It's the same thing. I can use this formula in black instead. Okay, it doesn't matter here. It really does not matter which way I solve this. Okay, so this is just a side note. You don't need to write this if you want to put it on the side for now. If I continue this line here, I can plug in knowing R1 was 0.04. V1 was 5. R2 is unknown. And V2 is 10. And then we can solve this for R2. And that's what R2 would end up becoming. 0.04 squared times 5 divided by 10, take the square root. Come on. Go for it.
I got 0.028.
Good. And that's in meters, so since we were starting in centimeters, probably makes sense to go back. What would that be in centimeters there?
Wouldn't it be 2.8?
Very good. She knows that centi means hundredth, so to go back, move it 2 decimal spots. It would be 2.8 centimeters. Now, I encourage you, if you think that these kinds of problems are too easy, or you're like, it's not bad, go back and do it again with what's boxed in here. Plug in for R1 as 0.04, V's on both sides, the V cancels. Okay, if you want to go back, V cancels here and here. The 2 remains on the right side, R1 is known, and you can just solve for R2. Another approach. Let's move on. Now, the next slide is called Bernoulli's Principle. In this section, here's what we want to understand. This is very, very, very counterintuitive. So if you think that, usually you use your instinct to answer a question, or on a test sometimes you're like, you know what, my instincts usually guide me in the right direction. This is one of those times where if you took your instincts, it's going to tell you to take it in the wrong direction. Most people think that when you put your thumb on the end of a garden hose, you're building up pressure, and you have a lot of pressure when the water flows out. The idea of building up pressure is right, but you need to recognize that the idea is that the pressure is higher back here. Pressure 1 at this location is greater than pressure 2. So again, the pressure in the fluid decreases as the fluid velocity increases. So although you think like, oh, there's a lot of pressure in the water coming out of the hose, there's really very little pressure in the water coming out of the hose. Where's all the pressure? It's in the water in the hose that's being backed up. Is that clear what I'm saying? Again, think about holding your thumb over the hose. Where your thumb is, behind that is a lot of pressure. When the water escapes, it's actually at much lower pressure. So as the cross-sectional area in this problem decreases, we know from the last problem, the velocity must get larger. So here, V2 is greater than V1. So in this problem, we want to write down that V2 is greater than V1. Okay, although the pressures are the opposite way, where P1 is greater than P2. So here's how I want you to remember this, because it really is counterintuitive. A lot of people think, oh, you must have higher pressure to create that faster water coming out. Yet when the water is going faster, it's actually the opposite. It's got lower pressure. So what could you say is the relationship between the velocity of a fluid and its pressure? How are they related? How are they related? What's the word you use? Indirectly, good. Inversely, I heard, or indirectly, the same thing. Indirectly or inversely. Okay, now, this is going to lead us into this next concept. This is how lift force actually works in airplanes not working. Go to your next slide, please. Go to your next slide, please. Okay, take a look at that diagram there. Somebody just read it nice and loud. I was going to point in the diagram, but it's not up on the airplane board. I'll point to it on mine, so later if you see it. Somebody read it nice and loud for us what we have here. Brian, go ahead, please.
The pressure, I'm sorry.
Next one.
The next slide.
Next slide. The force? Jake, help me out.
The force on an airplane wing is explained using Bernoulli's principle. Airplane wings are designed so that the airspeed above the wing is greater than the airspeed below.
So pause for a sec. I can't really point in the diagram. There's no airplane. Look at the diagram on your page right now. Look above the wing there. Okay, when you're looking above the wing, we're seeing that the airspeed that's above it is actually greater. That creates lower pressure. So write down low pressure, please. Write down low pressure on the top there. Below the wing, it's not on the board, guys, so if you have to be writing it down. Below the wing, write down high pressure, please. I'm going to reconnect the airplane right now, or try to again.
As a result, the air pressure above the wing is less than below. This imbalance of pressure creates a lift force in the upward direction known as the lift force.
Oh, I think I got it. No? There it is. Okay? So below the wing is higher pressure, above the wing is lower pressure due to the velocity of the air. The velocity of the air. Another word for this wing, by the way, is called an airfoil. So if you ever hear jot that down, that's actually the correct phrase for it. A wing is really an airfoil, is the word. Airfoil, one word. Again, the velocity is on top of the wing greater, so there's a lower pressure. Last slide for today. So notice, what is this section a lot of, by the way? A lot of? That too, but like instead of not math-based problems, conceptual ideas. 12-2 was a lot of math. The only math we've done was AV. That's really it so far. Okay, a lot of this is conceptual. This is where conceptual questions will most likely show up. Yeah.
You said wings are really...
Also known as airfoil. AIRFOIL. So this last thing is actually something new that I haven't taught in the past. This wasn't in old physics text, but in your book this year use it, and actually this is probably a good time for it. I would have actually probably included it in the last section because to me surface tension is a fluid at rest. How many of you have ever seen like a still lake? What do you notice in the top of the lake sometimes is sitting there? All over the lake in the morning before it's disturbed.
Is it like ripples then?
You'll see the ripples when it's disturbed, before it gets disturbed, or before anything gets touches it. What do you sometimes see sitting there all over the lake?
Like leaves and stuff like that.
You see leaves, what else? Bubbles?
Yeah.
Maybe some bubbles, but something else, a physical object.
was gonna say reflections.
You can see a reflection, yeah, that's true also. Sure.
Which
Think about the top and think about surface tension. Think about what that means and what I'm alluding to. Leaves are a good example, but leaves are interesting in their own sense. What?
Wood.
A piece of wood, yeah, for sure.
Is that like pollen?
Sometimes pollen, you see like those little like particles. But also, you ever see in the morning like mosquitoes and insects are always sitting on still water?
Yeah.
They are. If you've ever, they sometimes are, not always. But in like any wet area where there's like a little lake in the morning when it's really humid out, you'll see insects sitting on the surface. How can they sit on the surface? Think about it. They're not flying. We can. Can you stand on the surface? Can you walk on water?
Well,
All right. You see, yes, we're going to go to Jesus word right now. But you can't walk on water. How can insects walk on water? How is it possible?
well, they're so small and they weigh so little.
So what? A rock is very little, but it falls right in. Carolyn.
They're like really small and have like no weight if they run really fast.
Okay, so running helps for sure. When they move, it's easier. Absolutely, that's one part. So in motion, it makes it a lot easier to stay on that surface. It's because of this that the motion helps, actually. So think about this term.
Like the force acting up like the surface is more than like the force of the bug coming on.
Very good. That's exactly right. Well done. The surface tension acting up is greater than the force acting down. So surface tension is like, imagine this, ready? You ever go on a trampoline before? Imagine if you dropped a bowling ball on a trampoline. What would happen to it? Not from a high distance. You just placed it on there. The trampoline would do what? It would sag, right? It would sink. It would sag. Like, imagine in the middle. Put a bowling ball in the middle of a trampoline, it would all sag to the middle. That trampoline pulling back up is the equivalent of the surface of water. That's what surface tension is. Surface tension is like a membrane pulling you back up. Now, the membrane has an elasticity limit, a strength that cannot be exceeded. If so, you what? You fall into the water. Human weight is greater than an exceedable strength. The insect, those weight, is less. So the force acting down is less than the force acting back up. It's almost like a normal force. The water acts like a solid when compared to very, very, very light particles. Okay? That's what surface tension is here. What helps with surface tension? What's the bond between water molecules? What is it called? What kind of a bond is it? Yeah, but what's the type specifically? Hydrogen bond? Didn't you call it a hydrogen bond in chemistry? They were very strong bonds that held things together well. Surface tension, greater value in water there. If you put oil on the surface, I think, it decreases the amount of surface tension in the water itself. There's some sort of an experiment you do, either in chemistry or in forensic science with this. Might be forensic science with surface tension. Your homework, please, okay? Make sure to get this done tonight.